From winter hardwood harvesting and dangerous tree felling to high-capacity sawmills, firewood processors, and engineered wood systems, this is timber handled with intent. Watch raw logs become boards, panels, and structural strength through control, pressure, and precision. No rushing, no wasted motion, just machines, skill, and wood pushed to its full potential. Winter forestry places pressure on every decision made in the Odenwald, where frozen ground and cold air reshape how hardwood harvesting is approached. In these conditions, forestry is less about speed and more about restraint. Low temperatures change how trees respond to force, how equipment behaves, and how quickly small mistakes can escalate. Every action carries added weight when traction is unreliable and reactions are slower. Hardwood trees in winter store tension differently, and their fibers respond sharply to stress. Cold makes the wood denser and less forgiving, demanding greater awareness of how energy moves through the trunk. Snow and ice also compress margins for error, turning the forest floor into an unstable workspace where balance and positioning are constantly tested. Judgment becomes just as important as strength. The environment itself dictates the pace. Sound carries farther in cold air, visibility changes with frost and glare, and machinery must operate within narrower tolerances. Forestry crews adapt by relying on experience rather than routine, reading subtle cues in tree posture, wind direction, and canopy weight. These conditions reward calm decision-making over aggressive output. Despite the challenges, winter harvested hardwood maintains excellent structural integrity. The cold slows biological activity, helping preserve wood quality while meeting seasonal production needs. Timber taken from the forest under these circumstances reflects discipline rather than haste. In the Odenwald, winter forestry is not about conquering the environment, but working with it, accepting its limits and extracting value through patience, precision, and respect for the conditions. Risk defines every cut in Dangerous Tree felling by Jiri Buzek, where experience matters more than force. Unstable trees demand total awareness, with balance, positioning, and timing constantly under pressure. Wood tension, gravity, and terrain combine into a narrow margin for error. Decisions are made seconds ahead of consequence, not after. When the tree finally commits, there is no correction, only outcome. The brief silence before impact carries the weight of every choice made. Clean logs don't happen by chance when the Korwarka Forstchursk goes to work. This debarking system is engineered for reliability, handling a wide range of log diameters while maintaining stable output over extended shifts. Its design prioritizes uniform contact and controlled pressure, ensuring bark is removed cleanly without stressing the wood beneath. Consistency here is everything, because uneven processing quickly turns usable timber into waste. The machine's steady feed and balanced operation allow logs to move through in a smooth, uninterrupted flow. By reducing vibration and sudden load changes, the wood fibers remain intact and structurally sound. This stability supports downstream efficiency, minimizing rehandling and preparation time once logs leave the line. With productivity approaching 100 cubic meters per shift, the debarker quietly defines the pace of the entire yard. Operators concentrate on maintaining continuity rather than correcting problems. When the system settles into its rhythm, the process becomes predictable and controlled. That calm is not accidental. It's the result of machinery designed to do one job precisely, hour after hour. Order is visible, long before the first log ever reaches the saw line, at PPHU Grab Bud Adam Grabowski, Tartak Kresnozyelk. Timber handling here is guided by structure rather than urgency. From the outset, movement follows a deliberate logic that keeps materials flowing without pressure. Spacing, alignment, and preparation create predictability, allowing the entire operation to run without the tension that comes from improvisation. The yard itself sets the tone for what follows. Once alignment is established, the saw line becomes the backbone of the process. Primary cutting controls the rhythm of production, setting dimensions early and defining how efficiently everything downstream will function. Logs move through at measured intervals, producing boards with consistent profiles while reducing variation. This stage carries weight because any inaccuracy would repeat itself throughout the day. Precision here protects both output quality and operational stability. After cutting, freshly sawn lumber transitions into sorting and separation. Boards are organized by size, grade, and intended application, keeping incompatible materials from interfering with later stages. Transfer systems guide each piece smoothly, avoiding sudden stops that introduce damage or disorder. When sorting runs cleanly, downstream operations gain breathing room, and the entire line benefits from reduced friction. Preparation for drying follows, introducing a necessary pause in the process. Lumber is stacked to promote airflow and controlled moisture reduction rather than speed. This step preserves strength, shape, and long-term usability. By respecting drying conditions, the mill protects the value of the wood instead of sacrificing quality for short-term throughput. Time spent here prevents costly corrections later. Secondary processing refines the material further. Boards are adjusted, surfaced, and standardized to meet construction or resale requirements. These corrections are precise but restrained, adding consistency without overworking the wood. Repetition becomes an asset, creating a steady pace that reinforces control instead of fatigue. Before packing, quality checks quietly shape the final output. Boards that fail to meet standards are removed without disrupting the main flow. This selective filtering maintains reliability without slowing production or drawing attention. Decisions are made calmly, keeping the system balanced. Packaging and storage complete the cycle. Finished lumber is stacked, secured, and prepared for transport, with the same care seen at every earlier stage. At PPHU Grabbud Adam Grabowski, Tartak Kresnosielk, production is not about pushing wood through machines as fast as possible. It is about maintaining control while everything keeps moving, allowing order to carry the workload from start to finish. Turning a chainsaw into a portable sawmill changes the logic of how timber can be produced, especially when boards and beams are needed exactly where a tree falls. Mururisaha Sirkeli demonstrates how this kind of setup reshapes raw logs into usable lumber without relying on transport, heavy infrastructure, or permanent milling facilities. Instead of moving timber to the mill comes to the timber, and that shift alone redefines efficiency in remote or small-scale work. By mounting a chainsaw onto a circular sawing guide, raw cutting power is transformed into controlled, linear motion. What is normally a rough freehand tool becomes capable of producing flat, predictable surfaces suitable for planks, beams, and squared sections. The result isn't industrial speed, but precision that is good enough to matter. The cuts are straight, repeatable, and structurally reliable, which is the real requirement when lumber is meant for actual use rather than rough stock. Mobility is the defining advantage of this approach. Logs can be processed wherever access allows, whether deep in the forest, on uneven terrain, or near a construction site. This flexibility eliminates the need to haul heavy logs over long distances, saving time, fuel, and physical strain. It also allows timber to be milled while it is fresh, before handling, transport, or storage introduce damage to edges and fibers. As flat faces are opened and material is removed in measured passes, usable wood volume stays high. Smaller logs that might otherwise be dismissed as firewood can be converted into functional boards or beams. This controlled material removal helps preserve strength, making the most of each tree rather than sacrificing quality through aggressive cutting. The process feels efficient not because it is fast, but because little is wasted. One of the strengths of this system is adaptability. The same setup can shift between producing planks, posts, or long beams simply by adjusting cut dimensions. There is no need to swap machines or reconfigure an entire workspace. The saw guide keeps the cutting path stable over long distances, reducing deviation and ensuring consistency. That consistency is what determines whether the output becomes usable lumber or ends up discarded. Working directly at the harvest site also changes how wood is handled afterward. Boards can be stacked immediately for drying, protected from damage, or used straight away for construction tasks. There is a sense of continuity when timber is shaped close to where it grew, shortening the gap between resource and result. For hobbyists, builders, and small-scale operators, Mutori Saha Serkeli is not a replacement for industrial sawmills. Instead, it fills a different role, trading automation and volume for flexibility and control. It allows timber production to happen on demand, guided by judgment rather than production schedules. This approach keeps woodworking grounded in simple mechanics and direct decision-making. From forest floor to finished beam, the chainsaw sawmill shows how adaptable tools can expand what's possible without adding unnecessary complexity, proving that smart design often matters more than scale. At Sawmill Hardwoods, cutting oversized timber is about control, not shortcuts. Their custom-built bandsaw mill is engineered to handle material far beyond the limits of standard equipment, and in this case, it takes on a 45-inch pine log to produce a 4-foot-wide, natural live-edge slab. Logs of this scale bring their own challenges. Weight, internal tension, and irregular shape all demand careful setup because every decision made before the cut directly affects the final slab. Once the log is secured, the wide-cut bandsaw begins its pass with steady, deliberate movement. The blade tracks cleanly through the wood, holding a straight line across a span that most mills simply can't accommodate. A thin, properly tensioned blade removes minimal material, which helps preserve both yield and surface quality. This precision is essential when the goal is to keep the natural live edge intact rather than forcing the log into a uniform shape. As the cut opens, the character of the pine becomes visible. Growth rings, sapwood transitions, and grain flow remain continuous across the slab, turning the log into a single, uninterrupted surface. These features are what make wide slabs so valuable for tables, counters, and architectural elements, where the story of the tree matters as much as strength. This process is not driven by speed. The mill follows the log, responding to its form instead of fighting it. The result is a clean, consistent slab at a width few operations can achieve. At Sawmill Hardwoods, each oversized cut reflects craftsmanship at scale, where custom equipment and patience come together to honor the tree and unlock its full potential. Structural CLT wall elements take shape when the Express CLT system applies controlled, uniform pressure across stacked timber layers, turning individual wood components into a single structural unit. Unlike processes that treat boards one at a time, this system works on wide plate assemblies, allowing large XLAM wall panels to be pressed as complete surfaces. By compressing entire panels at once, geometry remains stable across their full width and length, which is critical when producing elements intended for load-bearing construction. The process begins with prepared timber strips arranged into longitudinal and cross layers according to the panel design. Some of these layers arrive as loose, individual strips, while others are supplied as pre-glued single layers. This flexibility allows the press line to adapt to different material formats without interrupting production. It also reduces bottlenecks, as layers can be prepared in parallel rather than waiting for a single fixed sequence. Cross layers are often assembled separately on a dedicated press before being transferred for final panel buildup. Once the longitudinal strips are side glued, they are stacked together with the cross layers to form a complete pressing package. Alignment at this stage is critical. Even load transfer across the panel depends on how precisely each layer meets the next. Any inconsistency here would compromise the panel's ability to act as a single, unified element. This stage quietly determines whether the finished CLT behaves like a solid slab or a collection of bonded parts. The full layup then enters the flat press, where uniform pressure is applied across the entire surface. Rather than bonding points or narrow zones, the system compresses the panel in a planar manner, maintaining consistent thickness from edge to edge. Adhesive cures under sustained, evenly distributed force, locking the alternating grain directions together. This cross-laminated structure is what gives CLT its strength, stiffness, and dimensional stability. After pressing, the CLT wall elements emerge as rigid plates ready for further machining or direct integration into building systems. The Express CLT line supports panels built entirely from loose strips, entirely from pre-glued layers, or from a combination of both. This mix-and-match capability keeps production resilient when material supply or panel specifications change. Structural performance comes from the layered system working as a whole, not from any single layer carrying the load. Rather than prioritizing speed, the system focuses on repeatable behavior and consistent quality across different projects. Panels leave the press without drama, flat, bonded, and predictable. From prefabricated cross layers to final planar compression, the Express CLT process shows how modern timber construction depends less on rapid output and more on controlled force applied evenly. That balance is what allows wood to scale up into reliable, large-format structural elements. These floor trusses come off the line straight, locked tight, and ready to carry real structural loads, and that performance points directly to the Four-Master Truss Assembly Machine from Alpine Equipment. The system is designed to reduce manual handling to the bare essentials, focusing labor on loading lumber, placing connector plates, and stacking finished trusses once assembly is complete. By concentrating effort where it actually adds value, the machine blends mechanical strength with controlled precision. The assembly table is positioned at a comfortable working height, which immediately changes how crews interact with the process. Reduced bending and lifting help operators stay consistent and alert through long production runs. Components are laid out and aligned on the table, held firmly in place while the gantry moves across the surface to press plates accurately and evenly. This stability ensures that joints are set correctly the first time, supporting long-term structural performance. Safety is built directly into the workflow. A warning light activates whenever the gantry is in motion, and safety bars stop travel instantly if contact is detected. These features protect operators without forcing production to slow down, allowing the line to run smoothly and predictably. The result is a controlled environment where attention stays on quality rather than risk. Once one side of a truss is plated, the floor master automatically turns the assembly, eliminating the need for manual flipping. This automated rotation keeps alignment intact and reduces physical strain. The machine can plate opposite sides of two trusses at the same time, maintaining momentum and minimizing idle time between cycles. Finished trusses are removed using a lift-out device that keeps material flowing without disrupting the workspace. Heavy-duty drive chains support consistent motion and reduce downtime, helping the system maintain a steady rhythm. With fewer people required to sustain output, production remains efficient and repeatable. The Floormaster proves that serious floor truss manufacturing depends not on more hands, but on smarter handling, safer motion, and controlled consistency. A keyed scarf joint cut into solid 8-inch by 8-inch oak shows how traditional timber framing solves problems of length, load, and alignment without relying on metal fasteners. This type of joint allows long structural members to be created from shorter timbers while preserving a continuous load path. Instead of interrupting strength, the joint redirects forces through carefully shaped contact surfaces. In post and beam construction, that ability to extend length without weakening the structure is essential, especially when working with large spans and heavy roof or floor loads. The joint shown here uses a splayed scarf layout with square under-squinted abutments, a form chosen for long-term performance rather than ease of cutting. The splayed geometry is not decorative. It plays a structural role by transforming tensile forces into compressive contact within the joint. As loads increase, the shape encourages the timbers to press into one another rather than pull apart. This inward force behavior is one of the reasons scarf joints like this have endured for centuries in heavy timber buildings. Before any cutting begins, layout lines are established across the timber faces. These lines define the overlap length, the splay angle, and the precise location of the keyway. Each line represents more than a measurement. It maps how forces will travel once the joint is assembled. Accurate layout ensures that contact surfaces meet evenly, allowing load to be shared along the grain rather than concentrated at a single point. In timber framing, good layout is structural insurance. Material removal follows in controlled stages. Rather than carving away aggressively, the joint is opened gradually, shaping each timber so they interlock along their length. This extended overlap is critical. By increasing contact area, stress is distributed more evenly, reducing the risk of crushing fibers or inducing long-term deformation. Even before assembly, the depth and length of the overlap make it clear that this joint is intended to carry serious weight. The splayed faces are refined next. Their angled geometry guides compressive forces inward, improving the joint's behavior under bending loads. Instead of allowing the beams to separate under tension, the splay encourages them to bear against each other more firmly as load increases. Square under-squinted abutments are then formed, creating mechanical stops that resist sliding in multiple directions. These abutments limit longitudinal movement and provide resistance against both gravity loads and lateral forces. Throughout this process, repeated test fitting plays an important role. The joint refuses to seat fully unless every surface aligns correctly. That resistance is intentional. It ensures that no single surface bears load prematurely, and that full contact is achieved only when the geometry is right. This careful refinement builds confidence that the joint will behave predictably once installed. Attention then turns to the keyway. A transverse pocket is cut to receive a hardwood key, positioned so it actively contributes to joint performance. The key is not just a locking pin. It converts vertical load into lateral pressure that draws the joint together. As weight increases, the key tightens the connection rather than allowing it to loosen. This self-tightening behavior transforms the joint from a simple overlap into a dynamic structural system. When the key slides into place, the joint begins to act as a single continuous beam. Dry fitting follows, allowing fine adjustments to achieve full surface contact. This step is critical because no glue or metal fasteners are used. The joint relies entirely on geometry, mass, and the natural behavior of wood under load. When assembled correctly, forces move smoothly along the grain, reducing stress concentrations and limiting long-term creep. Once complete, it becomes difficult to tell where one timber ends and the other begins. In post and beam frames, keyed scarf joints like this make long spans possible without requiring oversized, single-piece timbers. They allow builders to work efficiently with available material while maintaining structural integrity. The splayed form keeps compression working in favor of the joint, while the square abutments prevent unwanted movement. Nothing in the design is wasted. Every surface has a job. This build is not presented as a shortcut or a how-to, but as a clear example of how traditional timber framing solves structural challenges through proportion, force direction, and restraint. The joint does not demand attention once installed. It simply carries load quietly and reliably year after year. Seeing how much strength comes from shape alone makes it hard to overlook the intelligence built into these old solutions. What allows birch plywood to stay flat, strong, and consistent across thousands of identical sheets? Inside Rout's smart plywood manufacturing line, the answer lies in total process control. Every stage is synchronized to manage material behavior, bonding quality, and dimensional accuracy. Rather than relying on individual machines performing isolated tasks, the entire line functions as one coordinated system, where each step prepares the material precisely for the next. The process begins with birch logs prepared specifically for veneer production. Dimensions, roundness, and moisture content are regulated before the logs ever reach the lathe. This preparation matters because peeling accuracy depends on stability at the core. Route's automated peeling systems rotate each log while slicing veneers at a constant thickness, producing long, uniform sheets with minimal variation. Consistency here sets the foundation for everything that follows. Fresh veneers move immediately into high-capacity dryers. Instead of depending solely on time, Route's drying technology balances airflow, temperature, and conveyor speed to bring every sheet to a stable moisture level. Uneven drying would lead to warping or bonding issues later, so moisture control is treated as a structural concern, not just a finishing step. Automated scanning and sorting ensure that only veneers within target parameters move forward. Veneer composing and scarfing come next, where shorter or narrower sheets are joined edge to edge. This stage extends usable veneer length without compromising strength. Automated scarf joints align fibers carefully, allowing composed veneers to behave like continuous sheets. Once assembled, it becomes difficult to distinguish between original and joined material, which speaks to how precise the alignment must be. Defect handling follows through smart patching systems. Knots, splits, and imperfections are detected automatically, removed, and replaced with matching inserts. This step preserves both structural integrity and visual consistency. Instead of discarding material, the system recovers value by repairing defects in a controlled way. It's a quiet efficiency that keeps yield high without lowering standards. During layup, veneers are stacked in alternating grain directions, forming the cross-laminated structure that gives plywood its strength and dimensional stability. Route's layup lines handle glue application, veneer alignment, and layer sequencing with digital precision. Glue spread rates, spacing, and positioning are controlled to ensure uniform bonding. Each panel is built according to a defined recipe, making results repeatable across long production runs. Pressing is where the panel truly becomes plywood. Under controlled heat and pressure, adhesives cure evenly across the entire surface. Press parameters are adjusted automatically based on panel thickness, veneer count, and adhesive type. This ensures that bonding strength is consistent from edge to edge, preventing weak zones or internal stresses. It's the moment where separate layers lock together and begin behaving as a single engineered material. After pressing, panels move into trimming and sizing. Route's cutting systems deliver clean edges and precise dimensions, preparing panels for downstream processing or direct shipment. When required, overlaying adds protective or decorative surfaces, tailoring panels to specific applications such as flooring, furniture, or structural use. Final inspection systems verify thickness, bonding quality, surface condition, and dimensional accuracy. Only panels that meet strict tolerances continue forward. When every sheet exits the line looking and performing the same, the level of control becomes obvious. Birch plywood consistency at this scale doesn't happen by chance. It's the result of synchronized systems working at industrial speed, where every layer, every bond, and every cut is accounted for. Spindleless rotary veneer peeling changes how plywood cores are produced by removing the center shaft and allowing more of each log to become usable veneer. Instead of sacrificing material at the core, the process relies on direct roller contact to rotate the log with balanced pressure. This shift may seem subtle, but it dramatically improves yield while keeping the peeling operation stable and predictable. After debarking, logs enter the peeling machine where rollers grip the surface and control rotation without penetrating the center. This design adapts well to uneven timber, maintaining steady contact as the log turns. With rotation stabilized, the cutting knife advances at a fixed depth, slicing continuous veneer sheets at consistent thickness. Veneer exits in long, uniform ribbons, ready for drying and further processing. As peeling continues, the log diameter reduces gradually, converting nearly the entire log into veneer instead of leaving behind a large waste core. That efficiency compounds across high-volume production. When the target core size is reached, peeling stops cleanly, and the veneer moves downstream. The process doesn't rely on speed alone. Simple mechanics, controlled pressure, and steady cutting define why spindleless peeling remains a foundation of modern plywood manufacturing. A single plywood board, leaving the green defender line, carries far more than stacked veneers. It carries a sequence of controlled decisions that determine how it will behave years later inside real buildings. From the first cut to final testing, the process is built around predictability rather than appearance, focusing on how the material responds to load, heat, moisture, and biological threats over time. The journey begins with raw logs entering the facility, where they are cut down to manageable lengths and stripped of bark to expose clean, workable wood. Removing bark early isn't just about cleanliness. It ensures consistent peeling and prevents contaminants from interfering with later bonding. Once prepared, the logs move into veneer production, where they are peeled into continuous sheets. These sheets are then tenderized, allowing wood fibers to relax. This step reduces internal tension, helping veneers accept adhesive more evenly and behave consistently once layered. Drying follows, bringing moisture content down to carefully controlled levels. Veneers that are too wet or too dry introduce instability later in the process. Conditioning stabilizes the sheets further, ensuring they respond predictably under pressure and heat. At this stage, material behavior becomes more important than visual perfection, because internal consistency is what defines long-term performance. Core compositing brings selected veneers together with deliberate grain orientation. By alternating grain directions, the panel gains balance and strength, allowing loads to spread across the surface instead of concentrating in one area. Adhesive is applied using precision rollers that control spread rate and coverage. Rough cutting then brings panels into workable dimensions, making them easier to handle while preserving alignment. Calibration follows, trimming thickness across the panel to achieve uniformity before another controlled glue application. Pre-pressing lightly compresses the layered veneers, locking alignment in place before final bonding. This brief compression stage is critical. It determines whether layers remain cooperative under stress or begin to shift over time, creating internal weaknesses. Hot pressing is where the panel becomes plywood in the structural sense. Sustained heat and pressure activate the resins, bonding the layers into a dense, unified sheet. Uniform pressure across the surface prevents weak zones and ensures consistent strength from edge to edge. Once pressed, the board moves into nanochemical treatment, where protective compounds penetrate the structure. This treatment enhances resistance to termites and borers, changing how the plywood reacts when exposed to pests. Depth of penetration matters here, as protection must reach into the core rather than sitting on the surface. Printing follows for identification and grading, marking each sheet for traceability. Control testing then evaluates fire behavior, including flame spread, penetration, and burn rate. Watching plywood face fire tests like this reshapes how you think about interior safety. Results from these tests determine whether a board is suitable for higher-risk building zones or specialized applications. Before packaging, each sheet passes through final inspection to confirm it meets performance standards. The sequence remains consistent, because plywood reliability depends on discipline at every step. Green Defender plywood is not built around a single standout feature, but around predictable behavior under load, heat, pests, and time. That quiet reliability is why these boards are trusted in demanding environments, rather than used as temporary solutions. Logs approaching maximum mill capacity immediately change how operators think about clearance and control. The Woodmizer LX25 is asked to face a white pine that pushes every dimension close to its working edge. Large diameter softwood behaves differently once weight and width combine. That first pause before the blade moves says more than any spec sheet ever could. Initial hesitation often reflects respect for stored mass rather than uncertainty. Maximum capacity logs force every component to operate within tighter tolerances. The log measures roughly 10 feet long, with a large end reaching about 25.5 inches across, narrowing only slightly at the other side. Minimal taper helps maintain parallel faces through multiple passes. Straight grain dominates, broken by only a few knots, which keeps the cut predictable but still demanding. Fewer knots reduce deflection but do not reduce resistance. Positioning alone becomes a task worth respecting. Bed alignment determines how much correction is needed later. Logs this size don't allow casual adjustments once they settle. Gravity does most of the locking once the log is seated. Once seated, mass replaces friction as the primary stabilizing factor. Securing the log reveals the first real constraint. Holding strength matters more than holding height at this diameter. The rear log holds only reach about a third of the log's height, just enough to keep rotation controlled without full coverage. Partial engagement increases reliance on balanced pressure. Up front, the clamp barely clears the curvature, gripping higher than usual and leaving little margin. Clamp geometry becomes critical when surface contact is limited. This is where setup choices start deciding how smooth the rest of the run feels. Early alignment errors tend to repeat across every board. Limited clamp reach shifts more responsibility onto operator positioning accuracy. Once aligned, the LX25 moves into its cutting passes. Wide faces increase blade engagement time on each pass. The blade enters cleanly, maintaining a steady line across the wide face. Consistent entry reduces lateral stress on the band. Feed rate stays measured, letting the saw track through the pine without wandering. Uniform feed helps maintain thickness across the full width. There's relief in seeing the blade hold its path instead of arguing with the wood. Sustained tracking confirms the band remains stable under extended contact. After the initial slab comes free, the log is rotated for the next face. Rotation becomes easier once one flat reference surface exists. With improved access, the mill continues slicing boards consistently. Repeated passes confirm whether setup decisions were sound. Each pass produces lumber with uniform thickness, showing the LX25's ability to stay steady even when working near its maximum. Stability at this scale depends on machine rigidity more than speed. The white pine releases wide boards that stay flat as they leave the bed. Flat exit surfaces suggest even internal stress release. Seeing boards this wide slide off never really loses its impact. As cuts progress, the log steadily shrinks, reducing pressure on the clamps and holes. Decreasing diameter shifts load away from the highest stress points. Movement becomes easier to control, and rotation requires less effort. Later passes demand less correction than the first ones. The machine settles into a comfortable rhythm, repeating the same motion without deviation. Once the hardest part is behind, everything else suddenly feels cooperative. The output tells the real story. Board yield reflects both log quality and cutting strategy. From this single log, 13 boards measure 3/4 inches by 8 inches, matched by another 13 at 3/4 by 6 inches. Maintaining count consistency indicates stable thickness control. Thicker stock follows, including 4 boards at 2x3, plus single pieces at 2x6 and 2x8. Varying dimensions maximize recovery from remaining material. 2 final boards at 3x5 complete the breakdown. Pulling that much usable lumber from one log feels like a quiet win. Yield like this confirms that capacity limits were used effectively, not wasted. Throughout the run, the LX25 shows its limits clearly but without complaint. Operating near capacity highlights both strengths and boundaries. The clamps sit near their reach, the log holds do just enough, and the blade stays consistent. Balanced setup prevents small issues from escalating. This is the kind of run that teaches more about a machine than weeks of lighter cuts. The straight grain helps, but the size alone keeps attention high. Mass amplifies every small handling choice. Every pass demands focus, especially early on when weight and width dominate the setup. Early decisions influence every downstream board. Small adjustments matter more here than on average logs. Miss a detail at this scale, and the wood won't forgive it. As the final boards come off, the mill bed clears, and the log is fully converted. What remains is a stack of lumber that reflects both the material and the choices made along the way. This white pine proves that the Woodmizer LX25 can handle serious size when approached with patience and intent. Capability emerges when limits are approached deliberately. Scale changes everything, but control keeps it manageable. And yes, a perfectly straight 27-inch log might just fit next time. Coordination matters the moment the Blacks Creek Firewood Processor 2000B comes online, because efficiency here depends on flow rather than force. The machine is designed to handle cutting and splitting as a single, continuous operation, where stability and timing determine the quality of the output. Logs move through the system in a controlled sequence, and even minor disruptions can ripple through the entire process. What makes the operation effective is how smoothly material clears the work zone. Firewood exits cleanly and consistently, preventing congestion and reducing the need for manual intervention. This steady movement allows the processor to maintain momentum without frequent stops or adjustments, which protects both productivity and equipment over long shifts. As the rhythm settles in, the work shifts from reaction to observation. Operators focus on monitoring alignment, feed rate, and overall system balance, rather than correcting problems after they occur. When coordination holds, the process feels calm and deliberate. That sense of control keeps production moving forward, turning a demanding task into a stable, repeatable operation that lasts through the day.